Modern freight locomotives weigh around 200 tons and generate about 4,400 horsepower, yet they never plug into the grid. They make their own electricity every mile. The diesel engine under the hood does not drive the wheels directly. It drives a generator, and the generator powers electric traction motors bolted to the axles. That diesel-electric idea solved a problem that had stumped railroads for decades. Steam locomotives reached their limits in the early 1900s. Steam transmitted power through a direct mechanical chain, but if a steam engine stalled on a grade, it had almost no ability to restart itself under load. Railroad engineers needed a machine that could pull hard from a dead stop and keep pulling without stalling. Electric motors already did that well because they produce maximum torque at zero speed. The problem was how to carry enough electricity on the locomotive itself. The answer was to generate it on board. The idea took time to mature because railroads are conservative by necessity. They run on long-lived infrastructure, large capital budgets, and a deep tolerance for systems that have to work in winter, rain, dust, and heat. Diesel-electric traction only won once it proved that it could survive the same punishment steam had endured, while doing it with less crew labor and better fuel economy. General Motors introduced the first commercially successful diesel-electric locomotive in 1934. The diesel engine spun a generator, the generator produced electricity, and electric motors turned the axles. Within 2 decades, steam was essentially finished in North America. The core architecture has not changed since. The diesel spins a generator, the generator produces power, and the motors drive the wheels. A typical freight locomotive uses a large turbocharged diesel engine, often a V12 or V16 with a displacement around 68 liters. It runs at a relatively low maximum speed, around 900 revolutions per minute, because diesels are most efficient at steady load. The locomotive controls power by changing the electrical load on the generator rather than wildly changing engine speed. There are 8 throttle notches. Notch 1 is idle. Notch 8 is full power. Each notch changes how much fuel is injected and how much load the generator sends to the traction motors. That arrangement makes the locomotive feel almost like a power plant on rails. The prime mover does not need to race to the top of its speed range the way a car engine does. Instead, it stays in the zone where fuel use and torque are most favorable, while the electrical system turns that output into whatever the train needs at the rails. Inside the engine room, the sound is not a roar, but a deep rhythmic thump. Each cylinder fires in sequence around the engine. The block sits on rubber mounts to prevent vibration from cracking the frame. The turbocharger is essential. Exhaust gas spins a compressor that forces more air into the cylinders, allowing the engine to make far more power than its displacement would otherwise permit. Modern locomotives can boost intake pressure to more than twice atmospheric pressure, which is how a relatively slow-turning engine can produce thousands of horsepower. Cooling is a major engineering problem in itself. A locomotive at full power generates nearly as much waste heat as useful power. Coolant is circulated through the engine block and then through large radiators at the rear of the locomotive. Fans pull air through those radiators, and if temperatures climb too high, automatic systems reduce power to protect the engine. The engine is not just making power, it is constantly being managed thermally. Older locomotives use direct current generators. Modern ones usually use alternators, which produce alternating current that is easier to regulate and more efficient to generate. Rectifiers then convert that output to direct current for the traction motors. Under the locomotive are 6 traction motors on a typical freight unit, each paired with a gear reduction. The motors spin fast, the gears reduce the speed, and the axles turn the wheels. Those wheels are not simple circles, they are slightly tapered and have flanges on the inside edge. The taper, called the coning effect, keeps the train centered on the track without any steering mechanism. If the locomotive drifts to one side, the geometry creates a larger effective rolling diameter on that side, and the train naturally recenters. Steel wheel on steel rail, guided entirely by shape and physics. The wheel profile also reduces wear in a subtle way. On a curve, the wheel set can find a slightly different rolling circumference on each side without scraping hard against the rail. That matters because a freight locomotive may run thousands of kilometers across track that is never perfectly straight. The geometry is part of what makes rail transport so efficient compared with road transport. By the 1980s, locomotive cabs were changing too. Analog gauges and manual switches gave way to computer systems that managed fuel injection, alternator load, cooling fans, and traction motor current. Fuel use dropped, maintenance intervals improved, and problems that once appeared suddenly could now be predicted from sensor data. The locomotive was becoming less of a purely mechanical machine and more of an intelligent system supervised by a human. Modern locomotives also use distributed power. Instead of putting all the force at the front of a long train, the railroad can place locomotives in the middle or rear and control them from a single cab. That reduces coupler stress and makes very long trains practical. Some trains in Australia are more than 4 miles long. The engineer in the lead cab controls all the units by radio. Distributed power changed train handling in a major way. It reduced the compressive and tensile forces that can build up inside a long consist, which means fewer derailment risks on grades and curves. It also improved braking and acceleration, especially for unit trains carrying bulk commodities such as ore, grain, or coal. The train became a distributed machine rather than one giant push from the front. The cab itself is a carefully organized workspace. The engineer sits left of center. A combined throttle and dynamic brake handle controls acceleration and electrical braking. Separate controls manage the locomotive's own brakes and the train-wide air brake. Modern cabs also include event recorders, speed displays, positive train control screens, radios, and often forward-facing cameras. The cab is pressurized and filtered against dust and exhaust. Dynamic braking is one of the most elegant features of the diesel-electric system. When the engineer needs to slow down on a downgrade, the traction motors switch into generator mode. The moving wheels drive the motors, which resist motion by generating electricity. That electricity is sent to resistor grids on the roof of the locomotive, where it becomes heat. This keeps the friction brakes cool during long descents and can hold a train's speed for miles without touching the brake shoes. The resistor grids get extremely hot. Some are made from nichrome wire and can glow red during heavy braking. A single long mountain descent can dump more energy into those grids than a large house uses in a week. The system is deliberately rugged because it is meant to absorb huge amounts of energy continuously. Positive train control is the biggest recent safety addition to American railroads. It uses GPS, digital track maps, and wireless communication to enforce speed limits, stop signals, and switch positions automatically. If an engineer misses a signal, PTC takes over and stops the train. By 2020, all Class 1 railroads in the United States were required to have it active. It took years and billions of dollars to implement. Fuel lives in a tank slung under the locomotive frame. A typical tank holds about 1,400 liters of ultra-low sulfur diesel. At full power, the engine can burn around 220 liters per hour, though real-world running is usually less intense. Fuel efficiency is often measured in ton-miles per gallon, and a modern freight locomotive can move a ton of freight nearly 800 meters on 1 gallon of diesel, making it several times more efficient than a long-haul truck. The air brake system is older than diesel-electric power by decades, but it still matters. A continuous brake pipe runs the length of the train and stays charged at around 90 pounds per square inch. When the engineer reduces pressure, each car applies its own brakes using local reservoirs. The design is fail-safe. If the pipe breaks or a hose separates, the train automatically brakes. Stopping a 20,000-ton freight train takes a very long distance. That is not a flaw. It is physics. Electric power generated by the locomotive also feeds the rest of the train. Passenger locomotives supply head-end power for lights, air conditioning, heating, and food service cars. Modern locomotives can deliver hundreds of kilowatts for this purpose, enough to power a small neighborhood. Wheel slip remains a constant challenge. On wet rail, frost or leaf contamination, traction motors can spin faster than the rail can grip. Early engineers had to react manually. Modern locomotives use wheel speed sensors on every axle. If one axle spins, the computer reduces current to that motor within milliseconds. Sand helps too. Sand is blown from hoppers onto the rail just in front of the wheels, creating friction on slippery track. It is a century-old solution that still works. The trucks under the locomotive are more complex than they look. Each truck carries 3 axles and the traction motors. The truck pivots under the body through curves, and it carries more than 100 tons of weight. Bearings, center pivots, and suspension components are built to last millions of miles. Temperature sensors warn of overheating long before a failure becomes dangerous. Modern locomotives are full of diagnostics. Hundreds of sensors report coolant temperature, oil pressure, exhaust heat, wheel speed, brake pressure, alternator voltage, and much more to a central computer every second. Maintenance crews can see fault codes before the locomotive even reaches the terminal. The age of finding problems only by smell, sound, or touch is fading, though not gone. The same digitalization is making trains more autonomous. In Australia, mine haul lines have been running driverless trains for years. Rio Tinto's Pilbara network moves 240-ton trains over vast distances with no crew on board. The locomotives monitor every axle, every brake cylinder, every motor current, and every GPS position, while a central control room supervises the entire route. The system is no longer experimental. It has moved billions of ton-miles of freight. Picture a loaded iron ore train rolling through the Australian desert at midnight with no engineer in the cab. The computers are watching the track profile, the wind, the speed limits, and the health of every component. The train slows for a curve or a maintenance zone on its own. The technology is already here. What remains is the question of where it can and should be used. In North America, union rules and federal regulation still require a qualified engineer on freight locomotives. Supporters of automation point to the Australian results. Critics point out that sensors do not see everything, and that human crews catch problems no algorithm recognizes, especially in dense populated corridors. That debate is unresolved. Maintenance is its own world. A locomotive in service can cover about 200,000 kilometers per year. Every 92 days it gets an inspection and fluid checks. Every 18 months it goes through heavier maintenance. Every 8 to 10 years the engine is removed, rebuilt, and reinstalled. Almost nothing is treated as disposable. Crankshafts are reground, liners replaced, turbochargers rebuilt, injectors flow tested, and engines run on dynamometers before returning to service. Engineers learn the craft over years. They know grades, curves, crossings, braking behavior, slack action, and how different consists handle in different weather. PTC enforces limits, but experience still matters. The best engineers think miles ahead. What makes the locomotive remarkable is the balance it represents. It moves freight more efficiently than any other land-based mode, and it does so with an architecture whose fundamentals are almost a century old. Make electricity on board, drive motors on the axles, and control everything electronically. The industry has spent decades refining that idea rather than replacing it. Rail freight moves about 40% of US goods by ton-mile, mostly unnoticed. The locomotives doing that work carry grain, coal, chemicals, automobiles, and consumer products across a network of roughly 225,000 kilometers of track. They generate their own electricity, manage their own traction, monitor their own health, and do it with fuel efficiency trucks cannot match. The machine is evolving, but the core concept is still the same as it was in 1934. Diesel engine, generator, traction motors, power plant, computer, and robot all in one. It is one of the most durable engineering ideas ever put on steel rails, and it is still doing the job better than anything else on land. That durability comes from the fact that railroads solve a transportation problem that has not gone away. Moving heavy freight over long distances is still most efficient on steel wheels and steel rail, especially when energy costs matter. Diesel-electric locomotives fit that niche because they combine high torque, robust braking, and a power system that can survive rough service for decades. The operating culture around locomotives matters too. Crews are trained to hear changes in engine note, spot brake anomalies, and read track conditions that no sensor can fully explain. Dispatchers, maintainers, and engineers form a tightly linked network because a train is only as reliable as the people who keep its schedule, mechanical state, and route conditions aligned. As railroads experiment with smarter automation, the diesel-electric locomotive is not disappearing overnight. It is becoming the benchmark against which every replacement is measured. That is also why maintenance matters so much. A locomotive spends its life doing hard work in bad weather, so reliability is built through inspection, rebuilds, and constant measurement rather than through one-time perfection. Bearings, brake shoes, traction motors, wiring harnesses, and cooling systems all live in a cycle of wear and renewal. Railroads treat those cycles as part of the asset, not as an exception. The economics follow from that discipline. A machine that can run for decades, pull huge tonnage, and be rebuilt repeatedly is worth more than a short-lived vehicle with a lower sticker price. That long service life is one reason rail remains central to freight transport. The locomotive is not a disposable consumer product. It is industrial capital that gets used, repaired, and reused.